Hello, everyone. I am really excited to share our research with you all today, entitled Towards an Autonomous Robot-Based Laser Cladding Repair Process. I am Habiba Imam, and this presentation was developed with the help of Hamdan Al-Musaibali under the supervision of Dr. Rafiq Ahmed. To provide some context, my research deals with reducing waste. As we all know, waste generation is a natural product of urbanization, economic development, and population growth. In the year 2016, the global waste that was generated was 2.01 billion tons. This value is expected to increase by 70% in the year 2050. A recent report found that more than 60% of the non-hazardous waste comes from the manufacturing sector. With rising environmental concerns and growing public pressure, governments and industries are being forced to adopt sustainable manufacturing process. One such practice is repair. Repair essentially is a value retention process where a damaged component is brought back to like-new condition after it reaches its end-of-life state. Repair offers various environmental and economic benefits. It reduces waste production by 97% and offers up to 95% in cost savings. However, the current repair process is heavily reliant on a human operator. This makes it time-consuming, error-prone, and expensive. These issues can be tackled by automation. We developed a novel repair framework that automates several steps in the repair process. This here is our developed framework, where a machine vision system takes images of the damaged component and passes them through a deep learning model. The deep learning model essentially isolates the damaged region from the environment by creating a bounding box around it. This bounding box gives us two-dimensional information of where the damage is. Now, in order to make sense of that information in 3D or world space, we translate the 2D information to 3D information in a process called damage localization. Once we have our 3D coordinates, those coordinates are sent to a time-of-flight sensor, which acquires point clouds of the damaged geometry. These point clouds give us information of the damaged surface, and this information is used to generate a toolpath in order to repair the part. This here is an example of a repaired component. In order to do all of this, this is the experimental setup that we designed. The damaged component will be mounted here on the turntable. It's important to note that the camera and the time-of-flight sensor are mounted parallel to each other. This is done so that it makes it easy to translate the 2D information to 3D information. So the camera is going to be recording a video of the damaged component. This video will be sent to a deep learning model. The deep learning model will create a bounding box around the damage and isolate it. Once we have the two-dimensional information of the damage, we use a pinhole camera model to convert that to 3D world coordinates. These 3D world coordinates are sent to the time-of-flight sensor. The time-of-flight sensor then acquires the point clouds of the damaged surface. These point clouds are used to generate a toolpath. This video over here shows material being deposited in order to repair the damaged component. Now, what we're able to achieve from our framework is essentially individual automatic steps that are intelligent and are able to reduce the process time by more than 63%. Now, moving forward, what we aim or what we're hoping to achieve is performing all of these steps without human intervention, that is, in an autonomous setting. But that requires a deeper integration of the visual sensors into the robot environment and significant modification to the repair framework's logic. This brings me to the end of my presentation, and I thank you all very much for listening to me. And if there are any questions, comments, or feedback, we would be more than happy to take them in one of the breakout rooms. I hope you all have a great rest of your day, and thank you once again.